x in it. But that one is certainly not needed. I'm actually not even sure it's valid. Okay, these are the two additional axioms. Then we need one additional rule. And this again is the same principle as we saw for semantic tableaus. Namely, if I can prove phi of A and that A does not occur anywhere else in the formula, then I may conclude that for all x, phi of x. Again, this idea of having a fresh constant. You may ask yourself, no, that's the next slide. If you think back, the first thing we did with this Hilbert system is to introduce some auxiliary notation to make life a little bit easier. In particular, we straight away introduced the notion of assumptions, of being able to write something to the left of this turnstile symbol. And here also, if we do that again, then the rule for the universal must be careful, because this constant A must not only be fresh with respect to the formula that you want to quantify over, it must also be fresh with respect to all the assumptions that you have on the other side. So that's the generalization rule, that's the new rule that we have with respect to the propositional logic case. If you look at the rule over here, the rule that for generalization, something that may strike you is that it is actually a rule and not an axiom. So we have this axiom saying that for all x, phi x implies phi A. But we have a rule that says from phi A we may conclude for all x, phi of x. So you may ask yourself, could I not put that in the form of an axiom as well? Can't I just say phi of A implies for all x, phi of x? Would be much easier. Well, because Hilbert was such a clever guy, probably the answer is you can't do that. But why not? Why is this rule not equivalent to this axiom?
Maybe it has something to do with the constant not being fresh for the other part anymore?
That's exactly right, yes. You lose this freshness requirement in the axiom. And you can easily give an example where it goes wrong. For instance, I can say one instantiation of this axiom would be that because the number 2 is even, for all x, x must be even. Which of course is nonsense. Because I can all equally derive that the number 2 is indeed even, and therefore then that axiom would imply, using modus ponens, the axiom would imply that all numbers are even. And the point is that this constant, the axiom called A and now called 2, may occur elsewhere in your proof system, and therefore it is not fresh. If you put this in the form of an axiom, you can't actually you can't put the requirement that it must be fresh anywhere. So the rule works, but the axiom doesn't. Okay. We had this derived rule called the deduction rule, which was very helpful. The deduction rule said, if I want to show an implication, then I can do this by putting the left operand of that implication in my assumptions and try to prove the right operand of the implication. This is something that I think you used when you did the exercises. You should ask yourself the question whether that rule is still valid, because it's a derived rule. Now that the logic is more extensive, and the logic actually itself has a new rule, this generalization rule, does this derived rule still hold? The answer is yes, but I have to extend the proof that the derived rule still holds. How did I prove this result? I went through the proof rather quickly. I tried to impress on you how such a thing is proved. Do you remember? So, if it is a derived rule, then it must mean that everything I can prove with this rule, I could also prove without this rule. Yeah? So for all proofs that I can build with this rule, I could build a proof without this rule. Maybe the proof without this rule is much larger, that's why the rule is useful, but I could do without. So that's a proof showing that for all proof trees that I can build using this rule, I can also build a proof tree without this rule. So it's a proof that quantifies over all proofs. Yeah, it's a nice sort of thing that you are doing when you're doing logic. You're proving something about proofs. What is a proof? Well, a proof is a proof tree. So I'm actually proving things about trees. In particular, that gives me a proof method, that, namely the proof method of induction over the depth of the tree. So the way I proved this deduction theorem was by taking induction over the depth of the proof tree for this proof, and then showing that for all proof trees that use this rule, I can build an equivalent proof tree without this rule. So it was an induction proof. An induction proof has cases for axioms and for proof trees built using the only rule we had around, namely modus ponens. Now we have a second rule around, namely generalization. So that is the only extension I have to do. I have to extend my previous proof, the one that I did for propositional logic. I have to extend it with one case, namely the case that the proof that I built with this rule ends with the generalization rule. I don't think I will bother you with the details of this proof. I don't think that would be in any way helpful at this point of this day.
Would you also have to include the additional axioms in the base case?
Yes, you indeed have to, but there's essentially nothing to be proved for the axioms.
Yeah, that's right.
You could, you're right. You should do that, but
Yeah.
the proof is tricky. Okay, the proof is here on the slide and it's on the book, and I'm going to skip it. So the last thing that I want to cover today is that the Hilbert system itself is correct, like the Gensen system was correct. The proof that the Gensen system was correct. What does correctness mean here, by the way? This is something to think about. What does correctness of a proof system mean?
Was it not that in the case of Hilbert that if something was valid, we defined it as valid?
Yes. If it is valid, well, that is what correctness can mean. If you have a valid formula, then you can actually give a proof that formula is valid. Also, that would be the completeness of your proof system. Yeah? Then the soundness of your proof system is that if you build a proof, then the formula you prove is actually valid, which is the easier way, the easier part of the two. Well, given the undecidability of validity that I showed using the halting problem, is it possible that a proof system, any proof system, is complete in that sense?
No.
I assume that it would not be there.
No, because if I could indeed have an algorithm, if I could prove all valid formulas to be valid, then I would have an algorithm that decides validity. So it can't be true. But maybe it's true in a weakened form. So can we maybe weaken this statement of correctness such that there's hope that it can be fulfilled? Yeah.
Het kan zo'n zo voor a limited set of limited subset of the possible interpretations.
Of the finite invitations, you mean? Is that what you mean? Yeah, that gets us into finite model theory. I'm not sure that's. Oh, it's a good question. I don't know if that would work. Okay, this is also for me too late.
At least it's not the option you're looking for right now.
It's not the option I'm looking for, that's correct. No, I have to maybe go back on my words just now. If we have a valid formula, and we have a method that actually is able to prove every valid formula, this in itself would not give a decision procedure. Because that method, if you